So from the last class, we have been looking at the differential amplifier with active loads. So we started our discussion with a single-ended output, but we had a differently weird structure. Okay. So now for this structure, we have been asked to compute the differential gain, and we were using this GM as well as Rout method in order to compute those. Now, in the first case, when we try to compute the value of GM, we just shorted this node to the ground, and then we looked at the circuit whether the circuit is symmetric under this input condition. Now what we found is that we could able to see that there is a kind of heart shape that exists. It is something that we can draw a symmetrical line across them, and the circuit seems to be symmetric during the computation of this capital GM. So what is the value of capital GM that we got? It was GM, right? So with a negative sign, okay, and later we just try to figure out the computation or the value for this Rout, right? So now what we did is that we try to apply a small signal Vx and try to measure this Ix, right? So in this case, this node is not same as that of this node, because this drain of M1 is connected to the ground, whereas this M2 drain is not connected to the ground, but rather it is connected to some potential. Because of that, what happens is that the circuit loses its symmetry, and whenever the circuit loses its symmetry, we know that the node of this particular point Vp cannot be at 0, right? And what we did is that we just started analyzing what is the impedance that we look up and what is the impedance that we look down, and we got a final expression for it. Okay, so what was that final expression that we got? Okay, so when I look up, it was Rho4, but when I look down, what is the structure? Yeah, something like a source degeneration, but we finally got some sort of end result out of this. So I have this M1, M2, and I'm looking something like this, and both the gates are connected to the ground. Okay, so yeah, so we went on with a bigger expression. So let me label this as Rx. So what we know is that whatever the impedance that I see here would be magnified by the intrinsic gain of this M2, right? So the impedance that I have across the source of M1 could be written as 1 by GM1 parallel with Rho1, and this was being magnified by GM2 Rho2, and along with it we also have a resistance Rho2 plus this quantity. But later what I said is that the value of this 1 by GM is quite smaller than the value of R or R0. Okay, so in that condition, this quantity could be rewritten as just 1 by GM1, and even this quantity could then be replaced with 1 by GM1. Yeah, so now since both these transistors are same, both are having the same WL factor, what happens is that the GM of M1 would be same as that of my GM of M2. So due to which I can directly cancel out these terms. So among this first term, I would get Rho2, and here there is one more term which is again Rho2. But what about this guy, 1 by GM? So as I said, it is comparatively smaller than compared to the value of R0, due to which I can neglect this quantity. So the end result of this was twice the value of Rho2, and that is the result that we got whenever we look through this drain of M2. Okay, so these results are important for today's discussion, so that's the reason why I'm just trying to recollect all the expressions that we have done. So it was 2 times that of Rho2. And finally we got up some sort of conclusion out of the circuit, right? So the conclusions are something like this. Basically the circuit doesn't have enough gain just because the GM has been reduced by half. This is what the statement says. The current flows through this M1 is not utilized at the output, and due to which we end up having the capital GM to be just half the value of the transient GM. Okay, so now the solution for this is nothing but by using the current mirror structure in an appropriate way, rather than having the weird structure that I've mentioned here. We can actually use this current mirror structure in a much better way. So the solution of this, I guess everyone would have done it, is this particular structure, where I could able to see that I still use my current mirror structure, where M3 and M4 creates this current mirror structure, and then this is a complete structure that I have. Now let us see whether this structure is capable of providing me a capital GM that is equal to minus of GM1, 2. Okay, So this is what today's session is all about. But before we do that, first of all, we will do some sort of large signal analysis, and later I will just come back to the small signal gain expression, and later I will try to prove that the capital GM is going to be the GM1, 2 term. Clear? So I will start with this large signal, and then later we will move on to the small signal analysis. Okay? So in the case of small signal analysis, I will discuss about this quantity. Now your interaction is more important for us to really see the graph out of this particular circuit. Okay? So now that I just want to have a large signal analysis for a differential input. So what I really mean is that I'm just trying to have a differential input across this gate of M1 and M2. Now as you know that the differential input is nothing but VID could be written as V in 1 minus V in 2. Now I'm just going to vary this value of VID all the way from minus negative infinity to plus infinity. So when I have my VID that is negative, okay, or negative infinity, what happens to this transistor M1? Does it have enough value of VGS? Okay, so I think I'll just change this polarity here. I'll just make plus and minus here. Okay, so what happens is that just because my V in 2 is much larger than the value of V in 1, I have a negative value whenever I have this kind of situation, which means that I'm talking about a most negative value. So in this case, my V in 1 doesn't have enough value across its VGS to make this M1 to be on. So because of that, I will have this N1 to be under off condition. But what about my M2? And first of all, what is the current that flows here then? ID1? When M1 is off, yeah, this would be 0. Okay. Now what about this M2 and what is the drain current of it? Okay, so M2 is on. As I said before, if I want this VID to be negative, then I need to have this V in 2 to be a much positive value. So due to which it is on. But the question is my ID2 is ISS? Because if this is the current that flows here as ISS, is that current is the one that flows through my ID2? ISS by 2. No, but this transistor is completely off, right? It's supposed to be ISS, but you are all wrong. Let me try to prove that the current through this M2, even though it is on, it would be equal to 0. Now why is that the current is not equal to ISS and it is equal to 0? Now let us try to come back to the circuit and then see that when this particular transistor is off, okay, my ID1 is basically equal to 0, which means that what would be the value of this VGS for the M3? Yeah, VGS would be equal to VT. Yeah. Because we know that this diode connected structure can operate only in two regions. One is in saturation and the other one is in cutoff. Okay, only these are the two regions allowed for this diode connected configuration. Now, when you can say that this diode connected is working in cutoff region, whenever the value of VGS is equal to or less than VT. Okay, so whatever the value of VGS that I have is being again copied onto this VGS. Okay, so in this case, my M3 is also off. Just because the current is not drawn, which means that my M3 is off, cut off, and the same value of VGS is being copied onto my M4, which has the same similar setup. So due to which, what happens to my M4 then? That will also be off. Now, is there any path for me to make a current to flow from this point to this point? No, because all the three transistors are off under this condition. Okay, so under this particular condition, I have this M1 off, even M3 and M4 are all off. But what about M2? Is it on still? Yes, my M2 is on, but this guy is not drawing any current. So which region it has to be operating? Yeah, linear or deep linear region. Okay, yeah. So it is something like this. We have a graph which I can plot ID versus VDS. And we know that there is an enough VGS here, okay. So I have a particular value of VGS sitting across the gate of my M2. So due to which it can have a current, okay, for the given value of VGS to this M2. But there is no current flow through this device M2. Now under what condition I don't have any current is that when the value of VDS is exactly at 0, okay. So I have to be in this particular spot in order to have this current to be equal to 0, okay, which is nothing but the deep triode region. The transistor is on, but still I am in the deep triode region such that the current is equal to 0 in this case. Does it make sense? So now what about this M0 then? It also has a value of VGS which is greater than VD. But is this drawing any kind of current through this device? No. So even the current through this I0 is also equal to 0. Then which region is this M0 is operated in? In deep triode region. It also has to have the same similar setup. However, my M2 have the VDS value which is equal to 0. The same similar value has to be across this M0. Now, can you define what is the value of this Vout under this condition? Yeah, so why is that? Yeah, so no current is flowing, or you can just see from here. I don't have any current flow through this M0 transistor, for which I need to have the VDS supposed to be equal to 0. So whatever the source potential I have across this guy, supposed to be the same as that of my drain. Only then I have VDS equal to 0. Yeah, so the ground is available here. Now, even here, the VDS is equal to 0, which means that whatever the potential I have here has to be even available across the drain of this guy. Okay, so that is how the ground is being shifted here. Okay, so now under this condition, I have my Vout, which is equal to 0. Now, what happens when I try to step the value of VID closer to the value of 0? What happens? So ultimately, you end up having some sort of VGS across this M1. Okay, so the M1 will get into which region? So previously M1 was in cutoff. Obviously, when I move out of cutoff, which region we will end up having? Ultimately, it has to be in saturation. There is no other way. We can also think about this. There is a small amount of VGS, and due to which there is a small amount of current. Okay. Now, what is this potential then? It is nothing but VDD minus this VGS. So when this VGS is small, it draws a small amount of current, and M3 is also drawing the same small amount of current, which means that this value of VGS is also small. So it is VDD minus VGS is almost closer to a value which is equal to VDD. Okay, I have a drain potential which is quite larger than compared to the gate potential. Which region is then? Saturation. Okay, so you should know that whenever we move out of cutoff, we ultimately end up getting into saturation region. Clear? Yeah. So now because of that, let me also try to draw the currents. Okay, let me use this red one to draw the current of ID1. So the ID1 current is also 0 when I am having this VID in the most negative potentials. Okay, and I will also choose one more color for my ID2. Okay, even this ID2 was also equal to 0. The current that is flowing through this M2 is also equal to 0 when my VID is more negative. Okay, now ultimately when I try to increase this value of VGS, there is a small amount of current flows here. But what about the current here then? Will it be ISS minus ID1 or will it be equal to ID1? What is the value of ID2 in this case? Yeah. You see, whatever the current that flows in my M1 is always reflected onto my M2. Okay, but it is not always the case. Let me prove that. But the point is that since because the ID1 is rising, even my ID2 also will rise. Clear? Any doubt in this? Because there is a mirror structure that is sitting at the top. Okay, any current that flows through this has to be reflected over here, and because of that, the current, both the currents of ID1 and ID2 will start rising. So let me use my red color. So even this is also rising up. Okay, and at a particular point where I have my VID that is equal to 0, what is the current drawn by this M0? It would be equal to ISS, because ISS by 2 is coming here, ISS by 2 is coming here, and they add up together over here to create the total value of ISS. So now let me try to draw the current of this M0 with a green color. Now what happens is that as I move, these two current values are being added up. Okay, so due to which they quickly ramp up, and for the value of VID that is equal to 0, this current value would be equal to ISS. Clear? Because it's just the addition of these two currents that flows here. Any doubt in this regard? Yeah. So now, obviously, what happens the moment I have this VID that is moving away from to a different value, like a positive value? What happens under this condition? What happens to my ID1 in that case? Yeah, the VGS1 is keep rising in one end. Okay, due to which the current through my M1 has to be higher, right? It has to be higher. There is no other way. So I have to increase this current. Now, because there is a mirroring structure, what happens to the current through this ID2 then? The ID2 also has to increase, okay? But there is a kind of voltage that I need to consider here. Is this M2 transistor is capable of receiving that current, because the VGS across this device is not same as that of the VGS that I have here, okay? So even though it is trying to reflect this current of ID1 across this particular branch, this transistor doesn't have enough value of VGS to accept. So in that case, what would happen then? How will I reduce this current? You see, here, let me just go with the numbers, okay? So in this case, I have this 1.5 milliamperes, but the value of VGS that I have here is not capable of accepting this 1.5 milliamperes across the M2 transistor. So it is capable of accepting only 1 milliampere of current. Now, it's a mirror structure, but how these things can happen here? You see, I know that the M4 is trying to receive a value of 1.5 milliamperes, but bottom structure is not capable of accepting that particular current. So now what's supposed to be the drain and source of this M4 such that it can accept the value of 1 milliampere? The point is that, you see, even though the transistor is having a greater value of VGS, okay, it has enough value of VGS to draw a current of 1.5 milliamperes, but the bottom structure is not capable of taking those 1.5 milliamperes. It is capable of taking only 1 milliampere out of it, okay? So now what's supposed to be changed such that the M4 is also trying to take only 1 milliampere of current, the VDS value. You see, if the value of VDS is within this range, it has to accept this entire 1.5 milliampere. But if the VDS of this particular M4 is reduced, then it is capable of accepting the current even though the value of VGS is equal to this VGS, okay? So the way I can reduce the current through M4 is by stepping down the value of VDS to a small value such that it accepts that 1 milliampere current through it. Yeah, so let me come back to the same discussion. You see, I have a value of VGS across my M1 such that it draws a current of 1.5 milliamperes of current through the device, okay? Now, if that is the case, then M3 would reflect an appropriate value of VGS to draw the same amount of current. So let me label that as VGS3, okay? Now that VGS3, when I try to apply onto M4, then this transistor also has to draw the same current of 1.5 milliamperes through it, okay? So which means that I have a cara, something like this, where I have this value of ID4, where I have fed the value of VGS4 to be equal to VGS3. Now for which I need to get a current of 1.5 milliamperes, but the bottom transistor is on, but it is not capable of accepting 1.5 milliamperes, but it is capable of accepting only 1 milliampere current through it. So how it can happen is that if I could be able to reduce this VDS, okay, so rather than having a value of VDS over here, I am trying to reduce the value of VDS. So when I reduce the value of VDS, I am entering into linear region. So when I am entering into the linear region, then there is a particular spot of VDS at which I can still accept the value of current through this M4 as 1 milliamperes. But right now my transistor is in linear region. So now how is this trend goes on? Like let me try to plot this. So I have this value of Vout previously which was at 0, and then the Vout is keep rising. I got some mid value. Yeah, so let me look for the last condition where my VID is positive infinity. Now in that case, this transistor M1 is completely on, but what about my M2? It is off. So now what current flows through my ID1? Yeah, so it will be ISS, and even this guy will also be equal to ISS. Is that clear? Now it has created enough value of VGS here such that value of VGS3 is being copied onto my VGS4. Now this transistor is on, right? M4 is on, but since my bottom transistor is off, the ID2 is basically equal to 0. Now how I can make this current ID4 to be equal to 0 when it is completely on? When I am reducing the value of VDS all the way to 0, okay? So what is the potential of my Vout under this condition? Yeah, the VDS has to be equal to 0 means whatever the source potential I have has to be made available across my drain as well, okay? So that value would be equal to VDD. Yeah, so now in this case, what happens is that my ID1 current will flow to the value of ISS, but what happens to the ID2? The ID2 current would then step down all the way to 0. Okay, so the entire graph I've just reflected in the next page, and this is how it is. So this is the value of ISS. Sorry, it is not ID3, it is ID0. Yeah, it is ID0. Okay, yeah. So it is always a summation of this ID1 plus ID2. So whenever in this negative regime, both the currents are equal to 0. So the addition of both these currents would then lead to the same value of 0. But as you could be able to see, as I move towards the value of 0 VID, both these currents are adding up, and then they shoot up to a particular value of ISS when the VID is equal to 0. Okay, it's a summation. So the maximum value of this ID2 would then be equal to ISS by 2. Okay, this midpoint is nothing but ISS by 2 that is flowing across both the M1 and M2 transistor. Which one? Yeah. So this is the point where the slope is straight. Yeah, almost to this entire regime where the transistor is all in the saturation. But if I move out of this, one of the transistor would be in they will be in the linear or in cutoff. Yeah. No. The whole point is that the VID is a small signal. Okay, a small variation only you can apply for it. And differential amplifier is basically meant for sensing those small microvolt changes. Okay, so let me come back to the discussion of a common mode signal in a large signal analysis. Okay, so in this case, I'm not going to define how the currents are going to be defined through the structure. It is same as that of a differential amplifier with a resistive load. Okay. But the whole point is that I want to prove something which you have to remember for the entire semester. Only that I will do it. Now, I would argue that the voltage that I have here, Vout, is equal to VDD minus VGS3. Okay, or VGS3 comma 4. I want to prove that. Only that I will do today. But all our discussion remains the same when we discussed about a differential amplifier with resistive load. So I will not touch upon this completely large signal analysis for it, but the only thing is I want to prove this particular statement. Okay, yeah. So now, what is this differential input for this particular setup that I have here? 0. Okay, so I have my VID that is equal to 0, and now that the currents that are flowing through them would then be equal to what? Yeah. So from the previous graph, when my VID was equal to 0, what was the current that is flowing through my M1 and M2? It is both are equal to ISS by 2, and that is for sure. Okay, so I have this ISS by 2, and over here it is ISS by 2. Now let us have a condition where let me mark this particular node as VF, and for some reason the value of VF is greater than. So I have a value of VF that is greater than the value of Vout. Okay, so this statement, whatever I have written, can be proved only through contradiction. So I am making a contradiction stating that my potential of VF is larger than the value of Vout. Okay, so with that contradiction, let me try to prove that it is not so. It has to be VF and Vout has to be equal. Okay, so that is what my whole argument is all about. Now, in that case, what would be the current flow through this particular device if my VF is large? What is this VF first of all? VDD? Yeah, so VDD minus VGS3. Okay, so if I want to bring this particular node high, then which means that I have to reduce the value of VGS3, right? And the same VGS3 has to be copied onto this particular structure. Okay, so when I try to reduce this, what happens is that the current through this device will also reduce from the nominal value of ISS by 2. So let me mark this as ID1 that is smaller than the value of ISS by 2. Okay, now this in turn poses some sort of constraint onto this particular M4 structure. So then what current supposed to flow here then? Yeah, because I copied the same value of VGS3 onto my VGS4, then this also will be a current whose value is ID1, and this current is obviously less than the value of ISS by 2. But what about the tail node? What current is supposed to flow through them? But when I try to add both these currents, which are all smaller, can happen? No. Okay? Just because the summation of both these currents, ID1 plus ID2, has to satisfy this constraint. Okay? Now, if this has been reduced, even the current through this ID2 also gets reduced automatically, just because of the mirroring structure. So you could be able to sense that I have to have a condition where my VF has to be equal to my Vout. Okay? Only then I can have the addition of this ID1 plus ID2 end up having a value which is equal to ISS. Or in short, I have to have my ID1 and ID2 to be equal, and that value is supposed to be equal to ISS by 2. And I can have this condition whenever I have this VID that is equal to 0. Okay? It's a direct proof with a contradictory statements. Okay? So you can either assume this value of VF is smaller than the value of Vout or higher than the value of Vout. Okay? When you do so, you end up having some sort of contradictory result stating that I cannot have such kind of current flow. Okay? So with that contradictory statement, I am proving that Vout is basically equal to our VF. Okay? So which means that I will have a voltage which is equal to VDD minus VGS 3,4 always. Okay, I will just allow for some time for you to think in case if it is not striking you. Differential inputs. Differential input right now is equal to 0 just because my M1 and M2 are not having any differential signal. Okay, so they are being shorted to a common mode input. So I have fixed a common mode input value such that both these M1 and M2 are drawing this half the value of ISS by 2.
Equal to Vout for this, Vout should be VDD minus VGS.
Correct.
This is the normal equation, sir.
Yeah, correct. Yeah.
So for this condition to happen, like what are the conditions necessary? For VF equal to Vout,
Yeah.
what we need, sir? Like,
No, in the sense, like what I'm trying to say is that only at a particular single condition, you will have this currents to be equal to ISS by 2. Okay. In any other conditions, like if you take this one higher or smaller than this quantity, then those conditions will fail. So due to which, I'm just stating that whatever potential that I have has to be made available even here. Only then they satisfy. Otherwise, it won't satisfy. Just with a kind of contradictory statement, I'm proving it. So now what we do is that let us try for small signal analysis for differential input. Okay, I want to make a differential gain out of the circuit. Now the way that I'm going to evaluate the differential gain is again going to the computation of GM times R out. Okay, shall we try to do that? Yeah. So now what I do is that I just try to evaluate the capital GM first, and then later we'll try to evaluate the R out. Now what is the condition that I need to place when I try to apply or when I try to calculate the value of GM for the circuit? Okay, so the very first condition is that the output has to be shorted, and look for the current I out whenever I have this VID, right, or V in to the structure. So the similar structure has been replicated here, and this is what I have. I have my VID, and right now the question is that is the circuit is symmetric, so that we can apply all those results that we have got. Okay, so now the symmetry of the circuit is being observed right from the input, because a GM is something that relates my input to the output, right? So the capital GM is nothing but I out by VID. Okay, now from the perspective of this VID, I am just looking for whether this particular circuit is symmetric under its input condition. Now you have to tell me whether the circuit is symmetric under that condition. Looking from the gate of M1 and M2. When it looks, it is trying to see only the downward path. Okay, it is not, there is no connection from the gate to the drain, as you all know. Okay, so from the perspective of this, when I look down, I see the same node Vs, and from this M2 gate, when I see, I could able to see the same thing. Okay, so as far as this VID is concerned, the circuit seems to be the same. Either you stand from here or stand from here, it looks the same, it looks alike, which means that the circuit is symmetric. No, it is not equal to 0. Whenever I have a value of VID, I am looking from the gate of this M1 and seeing downward, because there is nothing that connects between the gate and the drain. Okay, because whatever the value of VGS that I have is connected to the current. Okay, so I'm looking only for that. There is no connection from the gate to the drain for any of the other conditions that I'm concerned. Okay, yeah. So either you stand from here or either you stand from here. The structure when I'm looking would be the same. Okay, provided the W by L of 1 and W by L of 2 are same. Okay, so under that condition, the circuit is symmetric from the perspective of my Vin or VID. Okay, so due to which I can bring this node to the value of 0. Whenever the circuit is symmetric, the very first statement is that when I apply an antisymmetrical inputs, then this common node would be brought down to 0. Clear? So now let us deal with what value of VGS1 I have to take and what value of VGS2 I have to take. Now what is the value of VGS1 that I have here? Yeah, so it would be plus VID by 2 because it's an antisymmetrical inputs, right? So if I have a plus here, what about the potential across this VGS? It would be minus VID by 2, and this VID equally splits. Okay, this VID is something like symmetrically it splits into two halves. If at all, if I have a different W by L factor here and a different W by L factor here, then I cannot split this VID into two halves. Okay, that is completely a different story. But as far as this circuit is concerned, I'm going to assume my M1 W by L factor and M2 W by L factor are same, and due to which the VID will be equally splitted, and it's an antisymmetrical inputs, due to which I have plus here and a minus here. Okay. Now, what is the current that flows through this drain of M1? How do I know? It's a small signal. We are talking about small signal. Okay, yeah. Okay, so it will be equal to ID1, small ID1, and that value is GM1 times the of VID by 2. Now, what about the current flow through this M2 then? Yeah, so I can write the current as ID2 that is equal to minus GM2 VID by 2, or if I flip the current flow, then I can just write this one as just plus GM2 VID by 2. Okay, I've just removed the negative sign and I flipped it. Okay, is that as clear? Yeah. So now we know that this structure, what is the structure of this M3 and M4? They are current mirrors. So any current flow here will also be reflected at this particular point, right? Now this current is equal to ID, yeah, that is equal to GM1 VID by 2. Now there is also one more current that is coming towards this node, which is again GM2 VID by 2. And what is the current, total current that flows out of this I out? Yeah, it is ID1 plus ID2, and the currents would be like GM1 VID by 2, and the other end I have GM2 VID by 2. Now both these currents are same, and if I assume that they are equal to GM1 is equal to GM2, then I can write it as GM1 comma 2 into VID. Okay, I have just added both the halves, and assuming that the value of GM1 is exactly equal to GM2, then I can just have a single term which is GM1 comma 2. Clear? Now, what is my capital GM out of the circuit? You see, from the previous case we had only half the value of GM1 comma 2, and right now when I remodified this load, then I could able to get the complete value of GM. Okay, and none of the current flow through this particular path is being wasted. Clear? Are you convinced with the way that I am just telling here, the symmetry of the circuit? The symmetry has been observed right from the input. Okay, so when I look for this VID, when I look at the gate of M1 and at the gate of M2, the circuit is symmetric. Okay, because of that, I could be able to bring down this node to the ground. Now, let us do the computation for Rout. Okay, so for Rout, what are the things that we need to take care? Okay, first of all, we have to remove the VID. So both the gates would be grounded. Now, apply Vx. Yeah. So this is the end result, right? Now, is the circuit symmetric? No. Where is my input for this? The input is my Vx, right? Because Rout is nothing but Vx by, sorry, okay, 1 by Rout or something like that. Okay, so basically some voltage source, and that voltage source is fed directly to the drain of my M2. Clear? So that is my input. Now I want to measure this Ix. Now with respect to the input, the circuit is not symmetric. The reason is that this node is not same as that of this node. Now you have to have a doubt in it. What is that doubt? What did I say when we discussed about this large signal analysis of common mode? Yeah, those two voltages has to be same. That is, what I said is that Vout has to be equal to Vf. That is what I said. But I never said the Vf has to be equal to my Vout. I never said that dialogue. Okay, it is always a one-way communication. Did I say wrong? Okay. So whatever the value of Vf has to be adapted to my Vout. Okay, but whatever Vout I have, yeah, so this statement is not always true. Like this part is not always true. Okay, did I say it wrong or the other way? The other way I said. Okay. Okay, so whatever the Vf that I have has to be adopted by Vout, but the Vout cannot adopt the value of Vf. Okay, the Vout cannot define the value of Vf. Clear? Is that making sense? This one? Because any voltage I can have, and it is not defining some sort of, I'm not defining a VGS to copy from here. It is always the copy is from M3 to M4. Okay, this cannot happen the other way because I'm changing only my drain. The change in the drain will not affect my VGS of this transistor. So I cannot impose this constraint from one end to the other end. Okay. Is that clear? So a Vout cannot define my Vf, but Vf can define my Vout. Okay? Yeah. So now, is the circuit symmetric right now? No, because I have a Vout that is equal to Vx right now, but this node need not to be equal to Vx. Okay, so this node is completely at a different potential. Because of that, the circuit is not symmetric from the perspective of my Vx. And whenever the circuit is not symmetric, what happens to the node Vp? That has to be cannot be equal to 0, right? So due to which I have this kind of structure. Now, how would we evaluate the Rout for the circuit? Huh? Yeah, so whenever I try to draw the small signal model, what happens to this ISS? It's open circuit, so I don't need to consider any of these things. Okay. Now the whole point is that in the previous case, when we had the structure, right? Yeah. So you can able to get back to the same structure. What is the impedance that I see through this drain of M2? 2 times that of R0 2. It is just not R0 2. It is twice the value of R0 2. So we know from this point to this point, from the drain of M2 to the drain of M1, I have a resistance, and that value of resistance is equal to 2 times R0 2. So I'm going to use that relation. Okay. So the equivalent resistance that I see from this point to this point is equal to this quantity. Now, how is that possible? Any contradictory, anything that is bothering you in stating this? Huh? Yeah, but the whole point is that whatever the current that flows into the drain of M2 has to come out of this. Only from that perspective I'm telling, okay? And after this, either it goes directly to the ground or goes through a resistance, doesn't matter. Am I right? So you see, if I have a resistor, this is 2R2, okay? Whatever the current that flows will come here. Whether this node is directly connected to the ground or connected through a resistance doesn't matter for me. This resistance is always equal to twice the value of RO2 is what I'm arguing, okay? Yeah, so I'm just going to apply that condition, and then that condition would give us, I have not drawn it. Okay. So what is the impedance of this, small signal impedance of this M? Okay, so I have a resistance whose value is 1 by GM3 in parallel with RO3, and from here to here there is a resistance whose value is twice RO1, 2, and then I have yeah. Okay, so I'm just going to visualize this Ix as a branch of 3 currents. Okay, is that as clear? Now, one of the current is through this path. Okay, path number 1. Okay, now because of this current mirroring structure, the same current would then be reflected here as well, right? On this particular node. Are you clear? Okay, so this current flow would then be reflected here through the value of VGS. Okay, so that is my second current. There is also one more current. What is that current? Yeah, so even the drain has a small signal resistance, right? And what is that small signal resistance when I look through the drain of M4? RO4. Now what is the current that flows through this device? It would be Vx divided by RO4 will give us the third current. So we basically have this Ix as a summation of 3 currents. Okay, one is this particular path current, the second one is the mirror of the same path 1 current, and the third one is the current flow through this RO4. Okay, so I'll stop here. I want you to compute this and come up with the answer. So we'll discuss about the answer in the 3:45 class. Clear?